this pre-calculus algebra video, we will solve some exponential equations, and we will solve some logarithmic equations. An example of some of the types of applications we can do are like this. Though it can be pitch black in the depths of the ocean, sunlight is visible as you get closer to the surface. About 12% of the surface sunlight reaches a depth of 20 feet, and about 1.6% reaches a depth of 100 feet. We can use information like this to solve some applications by applying the exponential function to determine the depths that correspond to various percentages of light. And in your textbook, you can find that problem worked out, the actual application problem, and then its solution, to get some ideas of the types of applications we can solve when we know how to solve an exponential equation. Now, here is an example of an exponential equation. We've got 4 raised to the 2x minus 1 power, and that's equal to 64. What we're going to do is rewrite the 64 as the like base of 4. Sometimes that works. Now, sometimes it doesn't work. So let me get you prepared for the time that it doesn't work. Here's a nice illustration I like to use. We've got a tree, and let's say that we have an X trapped up in the tree, kind of like a frisbee, your Nerf gun bullet, your whatever it is, trapped up in the tree. And how can you get that down? One way to get that thing down is to throw a log at it. How do we get an X down from the tree? We throw a log at it. So let me get the log. Oh my goodness, this is not a great drawing, is it? I was trying to do a branch on there to be a little more accurate, but let's just keep a basic log. We throw the log up at that X, and then what happens? The X falls from the tree. How do we get an exponent down? And when it's up above, we can throw a log at it. So eventually, the types of examples we're going to do, we'll have to throw a log. We'll have to use a log to solve this. But this one is a little easier, and you want to recognize that 64 can be written as 4 to the 3rd power, because 4 times 4 is 16, and 16 times 4 is 64. So because 64 is equivalent to 4 cubed, I could rewrite this equation, 4 to the 2x minus 1 equals 4 to the 3rd power. Do you see what we're going to do next? If these two are equivalent, the 4 raised to the 2x minus 1 is equivalent to the 4 third, then it must be true that 2x minus 1 is equivalent to 3. So now I can just solve for x. I'll add 1 to both sides. So we have 2x equals 4, and then divide both sides by 2 to get x equals 2. So the solution set is x equals 2. And we're using this property: if b to the m is equal to b to the n, then the two exponents. If the bases are the same, then the two exponents must be equal. Not every example works out so easily where we can get a like base. Here is another one that we can rewrite with like bases. Let me show you that arithmetic here off to the side. 8 is equivalent to 2 cubed. And then 16 is equivalent to 2 to the 4th. So I could rewrite this 8 as 2 cubed. Let me be really complete here. We'd have 8 x to the 8 to the x plus 3 equals 16 to the x minus 1. I can rewrite the 8 as 2 cubed, and I can rewrite the 16 as 2 to the 4th. So I'd have 2 to the 3rd to the x plus 3 is equivalent to 2 to the 4th to the x minus 1. Do you remember the power rule for exponents? If I have a raised to the r power raised to the s power, I'd multiply the two exponents r and s. So if I have 2 cubed to the x plus 1, that's going to be equivalent to 2 to the 3 times x plus 3, or 2 to the 3x plus 9. And if I have 2 to the 4 to the x minus 1, that's equivalent to 2 to the 4 times x minus 1, or 2 to the 4x minus 4. And now I've got like bases. We have a 2 and a 2. So it would follow that there are two exponents. The 2x plus 9 and the 4x minus 4 must be equivalent. So I could say that 3x plus 9 equals 4x minus 4. And if I solve this equation for x, I'll subtract 3x from both sides. 9 equals x minus 4. Add 4 to both sides, and I'd have x equals 13. X equals 13. So the solution set is 13. This is how we can solve the exponential equation by rewriting each side as a power with the same base. In this case, we used a base 2. In this example, we don't have a way to write 10 and 3.91 with the same base. We can't rewrite these as exponents. So here we go. We're going to get that x down from the tree by throwing a log at it. So let's throw a log at this at this exponent 10 to the x equals 3.91. Now we could use any log we want. We can use log base whatever. But since this is already written as a base 10, it's going to make the most sense to use log base 10, or in other words, to use common log. So what we're going to do is take this 10 to the x power and this 3.91, and we're going to do the log. And which log will we use? Let's use log base 10, so the common log. We'll throw a log at it. If we throw the log at the 10 to the x, to get that x down, we have to throw a log at the 3.91 also. And then using the exponent property, or the log property, remember that x would then fall down. So we have x times the log of 10 equals the log of 3.91. What is log base 10 of 10? So the base is 10. 10 to what exponent? Equals 10. Yes, that exponent's going to be 1, right? So this log base 10 of 10, or in other words, log of 10, is just 1. So we'd have that x equals the log of 3.91. We can do that on a calculator to get a really good approximation. And on my calculator, I'm using a Texas Instruments 30X. So if x is common log of 3.91. I'm going to hit log, and then the parenthesis opens up. I'll type in 3.91, close a parenthesis, and I'm going to get 5, that this is approximately, so exactly, x is equal to log 3.91, but approximately that's 0.5922. I'm going to just round, anytime I'm rounding, I'm going to just choose the 4 decimal places, and we'd have approximately 0.5922. Let's look at another equation we can solve. If we have 7 to the x plus 2 equals 410, and we want to solve this equation, we can throw a log at it. How do we get the x plus 2 in this case, down from the tree? We throw a log at it. You could use log base 10 or natural log. Since I used the log, common log last time, let's just use the natural log here. So we have 7 to the x plus 1, or x plus 2, I guess it is, 7 to the x plus 2 equals 410. If I do the log of both sides, in this case log natural or natural log, then this x plus 2 falls right off, like we had hoped. So we'd have x plus 2 times the natural log of 7 is equal to the natural log of 410. And now if I continue solving for x, I could divide both sides by the natural log of 7. So I'd have x plus 2 is equal to the natural log of 410 divided by the natural log of 7, and then I could subtract 2 from both sides to have x isolated as a natural log of 410 divided by the natural log of 7 minus 2. I could put that into a calculator to get an approximation, but if asked for an exact answer, it would look like this. And as an approximation, I'll type in ln 410 close parenthesis divided by ln 7 close parenthesis equals, and then subtract 2, and that's going to give me approximately 1.0917 if I round to 4 decimal places. That's how we can solve when the x is an exponent. We throw a log at it. If we have a log equation, we can put it in reverse and write it as an exponent. So if we have log base 4 of x plus 5 equals 3, then we'll have 4 to the exponent of 3, because remember, finding this log gives us the exponent. So the 3 is the exponent. So 4 cubed equals x plus 5. I could do 4 times 4 times 4 to get 64. 64 is x plus 5. Subtract 5 from both sides to get the x equals 59. X equals exactly 59. Log base 5 of x plus log base 5 of 4x minus 1 equals 1. Here's where we're going to need to condense this log into a single log. I'm going to condense the log into a single log. Let me clear a little of the space here. So I'll use the product and quotient rules of logs. In this case, the product, because they're both positive, it's log base 5 of x plus log base 5. They're both the same base, so I could rewrite this as, sorry, the picture's moving around on us. So I'd have, if I rewrote this as a single log, log base 5 of x plus 4x minus 1. So we'll multiply this. We have the log base 5 of x plus log base 5 of 4x minus 1. So when I write this in its condensed form, I'm going to multiply x and 4x minus 1. So we'd have log base 5 of 4x squared minus x. I've distributed the x, or I've multiplied x times 4x minus 1, and this equals 1. Now I can rewrite it as an exponent form. 5 to the 1, or just 5, is 4x squared minus x. Solve this quadratic equation by setting it to 0. So when I factor that, 4x squared minus x minus 5, I get 4x minus 5 times x plus 1. Setting each factor to 0, 4x minus 5 is 0, or x plus 1 is 0, I'd get two solutions, x equals 5/4 or x equals -1. But be careful, we're not done yet, because we have to be mindful of the domain, right? For the domain of x, we'd have that x, because we're doing logs, x has to be greater than 0, and 4x minus 1 has to be greater than 0. And this x equal to -1 falls outside that domain, so I'm going to reject that. I'm going to check the domain and then reject the -1, so our solution is only that 5/4. Let's try another equation. If we have log base 10 of x plus 4 minus log base 10 of 2 equals log base 10 of 5x plus 1, I could condense the log x plus 4 minus log 2 by rewriting that log of this quotient, x plus 4/2. And because the base is the same for all of these, I could now say then that the x plus 4/2 and the 5x minus 1 must be equivalent. Notice that the first step was that I condensed this into a single log on the left by using the quotient rule for logs. And then I can use the 1-to-1 property to say that x plus 4/2 is equivalent to 5x plus 1. If I multiply both sides by 2, I'd have 10x plus 2, so x plus 4 equals 10x plus 2. I could subtract x from both sides and have 4 equals 9x plus 2. Subtract 2 from both sides and have 9x equals 2. Divide both sides by 9, and that gives us that x is equal to 2/9. Looking at our domain, if we check this, check the domain, we have to have x plus 4 greater than 0, so x has to be greater than -4, and we have to have 5x plus 1 greater than 0, so 5x is greater than -1, x is greater than -1/5, and with x being positive, we're in the clear with the domain. So it looks like we can keep our x equals 2/9. When we know how to solve an exponential equation, we can then solve some important application problems. Here's an example using growth. Formula A equals 37.3 e to the 0.0095 e models population of California, A, in millions, and this is in T years after 2010. When did the population reach 40 million? If the population reached 40 million, then A is the 40 million. So A in millions is population, so we're given that A is 40. And when did this happen? We want to find the time. We can find the time by replacing 40 for A. I'm just noticing a misprint. I don't know if you saw this in your notes, but this E really should have been a T. If you want to change that on your printed notes, I'll contact the publisher about that also, but the formula should read 0.0095 T. All right, now that we've got that, we're ready to solve for T. Here's an interesting piece to this is before I throw a log at this, I'm going to simplify as much as I can. And to simplify this, I'm going to divide both sides by the 37.3. So it would look like this. I'd have 40 divided by 37.3 equals e to the 0.0095 t. And now I'm ready to throw a log at it. When I do the natural log of both sides, I have the natural log of 40 divided by 37.3. Now be careful that you're not seeing that as natural log of 40 divided by the natural log of 37.3. So we did the log after we divided, so it's the natural log of that quotient. And the natural log of e, this exponent is going to fall down, so we'd have natural log of 40 over 37.3. Don't put that in your calculator yet. You don't want to round that yet. And then this exponent would fall down, 0.0095 t times the natural log of e. And the natural log of e, we're saying e to what exponent equals e? Well, that's a 1. So this natural log of e is just 1. So to solve for t, I could now just divide both sides by 0.0095. And when you put this in on your calculator, I'm going to use the Texas Instruments 30X. I'll put ln, the first parenthesis opens, I put 40 divided by 37.3, and then close parentheses. And then divided by 0.0095, and I'm getting that t is 7.3564. If t is the years after 2010, and this is asking for a year, when did the population reach 40 million? I could say that the population hit 40 million 7 years after 2010, so that's in 2017. 7 years after 2010 is 2017. Let's rush through one last example using a common formula. This problem is asking us to find the time, so how long does it take, when we have an account where the interest is compounded continuously. The continuous compounding formula is A equals PERT, P times E raised to the RT power, so A equals PE R to the RT. And here's the steps that I'm encouraging you to use each time. Don't take a shortcut here. Don't take a shortcut and then actually end up costing yourself more time. Just follow each of these steps. Number 1, write the formula. I know the formula is right here, written already, but write it out. A equals PE to the RT. I hope you're writing that on your note paper. What do we know from this problem? What are they giving us? They're giving us that it'll take $35,000 to grow to $70,000. So our initial principal P is $3,500, and the amount it's growing to is $70,000. A equals $70,000. We've got an annual interest rate of 8%. 8% is 0.08 as a decimal. So we know these three values. When I go to step 3, I'm going to fill those in. So in place of A, I'll write 70,000. In place of P, I'll put the 35,000. In place of the interest rate R, I'll put 0.08, and then I'm going to solve for T. How do I solve this? I'm going to start by simplifying it. So I'll divide both sides by 35,000 and we'll get 2, right? 70,000 divided by 35,000 is 2. So we have 2 equals e to the 0.08t. Just to make this really clear, this isn't, if I was using paper, what I would do is turn to a new page. But what I'm going to do here is just copy this over to the left. So we have 2 equals e to the 0.08t. How do we get that t down from the tree? We throw a log at it. Which log is going to make the most sense in this case? Any problem that we have an e, we want to use the natural log, the log natural. So we have the natural log of 2 is equal to the natural log of e to the 0.08, and that exponent falls out down to the ground, so we've got 0.08t times the natural log of e. The natural log of e is just 1, because e to the 1 equals e, and remember the log is finding the exponent, so what's the exponent? Exponent is 1. Natural log of e is just 1. So we have the natural log of 2 equals 0.08 times t. If I divide both sides by 0.08, I've got the answer. The t is exactly natural log of 2 divided by 0.08. And then if I wanted an approximation, I can put that into my calculator. I'm going to use my calculator, my Texas Instruments 30, and say ln2, close the parenthesis, divided by the interest rate, 0.08, gives me 8.664, which if I rounded it to the nearest tenth, it'd be 8.7, to the nearest hundredth, 8.66, to the nearest thousandth, 8.664. But it's it looks like this account will reach 70,000. So in other words, it will double in 8.6 years. And that wraps up our section on equations. Here are all the properties put together. If you want to pause and add any of these to your notes, could be very helpful to you. But I hope that this video on solving exponential and log equations was helpful to you. Please let me know if you have any questions that you'd like to go over further.